since I was a little kid, I've been fascinated by how objects are built and how that relates to their function and application in everyday life. I was that kid who tried to take apart all of my toys and even just random objects around my house because I was either trying to improve them or figure out how they worked. My innate curiosity resulted in several broken appliances all around my house, and because I lacked any real knowledge, I couldn't put these objects back together once I'd taken them apart. Eventually, it got so bad that my parents actually had to hide the screwdriver set from me. But even that didn't stop my curiosity from getting the best of me. Here I am now, 13 plus years later, and that aspect of me still has not changed. Obviously, I don't go around and try to take apart all the appliances in my house anymore, but I am constantly thinking about ways to improve the objects and structures I see every day. I consider how I can make them more cost efficient, more user-friendly, more innovative. Hi, my name is Cynthia Kanabarku, and my field of study this year in ISM is Biomedical Engineering. Now, when I first chose to study Biomedical Engineering, I really didn't know that much about the field itself. Since it is a relatively new subset of the field of engineering itself, most colleges and universities have only recently incorporated this as a major offer there. So, the field is still in its growing and adjustment phase. What is biomedical engineering, you might be wondering? Well, it is the application of engineering principles to solve medical problems and advance medical care. And if you're thinking that definition sounds extremely vague, you're absolutely correct. Biomedical engineering kind of serves to merge the gap between medicine, as in being a doctor, and manufacturing and industry, which incorporates more engineering design tools. So, as a result, prospective biomedical engineering students need to be equipped with a vast array of skills in order to be successful in this field. In this way, biomedical engineering overlaps with several other fields of engineering themselves, like mechanical engineering, electrical engineering, and even chemical engineering. And because it's so diverse, it incorporates several other subtopics. Some of these subtopics are biomechanics, which studies how objects work in relation with one another and interact. Another is medical imaging, which is all about how can you get the most crisp representation of the human body onto a digital screen. Another is nanotechnology, which, like its name sounds, is all about making technology as small as possible while retaining all of its functionality and keeping it efficient. Another is tissue engineering, which is actually a relatively new subset, and I'm actually going to be talking about this more later. And the last is biomaterials. Now, the materials you introduce into the body, you want them to be non-lethal, obviously, and non-carcinogenic. So you want to make sure they're degradable and that they are fluid, so they don't impair normal body functions. So out of all of those subtopics I just listed, my two main interests at this point are prosthetics and biomechanics and tissue engineering. I actually found the field of biomedical engineering itself through prosthetics. That's how I learned about this field. So when I think about prosthetics, I think about how closely can you replicate a human body part? Because you're essentially trying to give a user back some of their normalcy of life. Take, for example, an arm prosthesis. This individual no longer has any control of this arm. So you're trying to build a device that can accurately replicate and function with the existing nervous system, muscular system, and skeletal system. So when you're designing a prosthetic, you need to make sure that you're making it work well with the existing body parts and that it's actually adding utility to that user's life rather than taking away some usage. The other main topic that I'm really interested in is tissue engineering, which is all about growing entirely new functional artificial organs from a couple of cells in a scaffold. Now, a scaffold is just an organ that is used as a basis for growing these cells on. So when you think about trying to regrow a heart, a scaffold could be a human heart, or it could be even a pig's heart, because it doesn't have any of the human diseases, so it's almost better sometimes to use that as a scaffold. So you take this scaffold and you drench it with detergents to remove all the existing cells, and then you put in the individual cells and you induce it with growth factors. And as those growth factors multiply and you put it under the right environment, you can actually create an entirely new organ. Obviously, this process is a lot more complex than I just made it sound, and especially with something as complex as a heart, it's very difficult to make all these different systems of cells grow together in unison to produce a cohesive, functioning heart. But once we do figure that out, it will be absolutely amazing and really help out in the medical field. Now, the second component of my ISM experience so far that I want to talk about are my research interviews with professionals that I've had. So far, I've been on 5 research interviews, and I actually have another one coming up this week. And what I've taken from these research interviews is that there are so many different professions out there I can pursue within just this field itself. Take, for example, my first interview with Professor Hayenga. Now, she specializes in cardiovascular research and imagery. And what she really focuses on is atherosclerosis, which is all about calcium deposits and blocked arteries. She has her students gather information from a lab setting, and she incorporates the data acquired from that lab setting into a computer program and creates an algorithm for it. Now, the entire purpose behind doing so is so that any patients at the clinic she works in conjunction with, she can assess their diagnostics, input them into this algorithm, and then determine their future risk of blocked arteries, which is really important because insurance doesn't start to cover the surgery until the blockage is at 70% or more, which obviously at that point it's extremely critical and you need to make sure you're diagnosing it and assessing the situation correctly. So the more research and data she acquires from a lab setting, she can make this computer program more accurate and better predicting of the future risk levels. Another interview that I had was with Dr. Cersei, and he actually focuses on neuroblastoma and how to direct cancer treatments directly to the affected cells so that you're not killing healthy cells in the process. Because if you kill healthy cells instead of the ones that are actually sick, you could actually be hurting that individual more than you're trying to benefit them. So if he's able to specifically target the affected cells that have cancer rather than all the individual's healthy cells, it will be a better treatment overall. So that's kind of what he's researching at this point. Out of all the interviews I've had so far, the 2 I really want to focus on are my one with Mr. Wilson and then my other one with Dr. Eberhardt. So my first interview that I want to focus on was with Mr. Wilson. Now, Mr. Wilson is at UT Southwestern, and he specializes in prosthetics and orthotics, which is another subset of engineering that I've never even heard of before. So what he does is he actually works directly with patients in a clinic, creating prosthetics and orthotics for them. So the difference between a prosthetic and an orthotic is a prosthetic is meant to replace a lost limb, while an orthotic simply braces an existing limb and just supports it because it's not working at its full capacity. So in my interview with him, he actually gave me a lab tour of the one they have at UT Southwestern, which was absolutely incredible. I got to see so many different components of this process, from its initial stages of working directly with the patient to giving them this finished product that they can then implement in their daily life. So the first step is casting. Now in this step, they take measurements of the residual limb, which is the limb on which the prosthetic rests. So because he works with lower limb prosthetics, the residual limb is his upper thigh. So they take measurements of the patient's residual limb, and they wrap it with plaster bandages and mark the bony areas. And after this hardens, they can remove this cast, and they use it for the second step, which is filling it with plaster of Paris and creating a positive model. And with this, they add plaster to bony areas and take away plaster from soft tissue areas. Now the third step is pulling. Now with pulling, they heat up a plastic sheet to extremely high temperatures in an oven and drape it over this positive model. And they pull a vacuum on it so that it's airtight and has no holes in it. And after this cools and hardens, they can cut around it, and they have this thing they call a socket now, which is essentially the prosthetic they've been trying to design. The fourth step is alignment. This is when you, as you can see in the image on the right, you use that pylon to make sure that the way you're designing this prosthetic matches that patient's anatomy. Because you don't want it to have a perfectly straight prosthetic if that patient might be bow-legged, for example. And the last step is the foot attachment, which is the little piece on the bottom, and this varies depending on the patient's lifestyle. Another thing I learned in my interview with Mr. was about targeted muscle reinnervation, which is a new technique in which a surgery is involved and you remove some of the muscles in the arm and you attach it to a bicep or tricep. And then after you give the patient a rest period, maybe a month or 2 months, you can actually reattach these nerves to a prosthetic arm, and it's almost like they have an arm that works just like a natural arm would, which makes it a lot easier to use and better functioning. The second interview I want to focus on was with Dr. Eberhardt. Now, Dr. Eberhardt started in this field in 1964, so he has a lot of experience and really showed me just how much this field has changed from when there were basically no regulations for how medical devices were designed and produced to now it's extremely regulated. And he told me about some different failures of engineering in the past and how engineers have had to recover from those failures, which taught me in order to be successful in this field, you need to have an open mind. You need to be willing to work well with others, and you need to be willing to see other people's perspectives. So you need to be creative and come up with new ideas all the time. And that brings me perfectly to my quote for this year. What material success does is provide you with the ability to concentrate on other things that really matter. And that is being able to make a difference, not only in your own life, but in other people's lives. Oprah Winfrey. Now, just like this quote says, I want to use all the experience and knowledge I gained this year in ISM and over the course of my college education to directly impact people's lives and make it better. This field has so many opportunities and possibilities for me to directly impact the world, and even though I still have a lot more to learn on my ISM journey, I do know this. Biomedical engineering combines creativity with basic engineering principles to actively improve other people's lives and advance medical care. And I personally can't think of a better way to improve life than through technology itself.